Got it on me, on me. My life is cold. On me, on me. Whoa, I want to hear the slow down reverb real quick. Oh yeah, I like that. I think what I want to do is put it at the end, compare it to its parent. Actually, let me get the lane. Do something like that. I'll be comparing that. In this case, it'd be a parent node. Let's create like a current index, parent index. We don't need child. Current, while current. Got it on me. On me. While it's greater than 0. Because if current index is at 0, it's at the top. push this up here. I like this better, actually. Yeah, it's a little more organized. I know this is not going to change, but I'm going to just say let, so it's consistent. And I guess we want to break if this dot values, we want to keep pushing it up. We want to break if so if we push it to the end, for example, so we have like so we're going to use the site board. So we're going to have an array. It's a minimum binary heap, right? So it's going to look like something like that. Add 3. Notice how we're adding it to the end first. Now what happens if I add 2? First thing we want to do is add it to the end. And then we want to check, this is current, and this is parent. Okay. Now since current is less than parent, we want to swap them. So I'm getting something like this. Now, this is a valid minimum binary heap. And we're looking, well, we see the parent is less than or equal to current. So at that point, you're good. So if parent index is less than or equal to this dot values current index, we're good. We can break from that. Our parent index is going to be, now to get the parent, so remember to get the child, if I want to get 1, or if I want to get 1's right child, that's 2n, where n is the index of 1. So n plus 2 to get the right child, and it would be plus 1 to get the left child, right? So I want to access 7 in the array. Our array is our heap. We're going to use pointer manipulation to sort of resemble this sort of structure. And so if I do 2n plus 2, well, we look at the element 1, its index is at 0. So we just access the index 2, and that'll give us the right child, which is 7. Okay, so that's how we access the child. Now, if we're at 7 and we want to access its parent, now 7 is at index 2. So if I want to access its parent, I can take 2 minus 1, take 1, divide that by 2, and then floor it. So round down. That'll get me 0, because this is 0.5. Round down, that gets you 0. Okay, so you take current index minus 1 divided by 2. Let's go ahead and put this right here, and then let's floor it. Math.floor right here. Now we have our parent. So what we're going to do here is, if it's the case that the parent is, sorry, this should be, if the parent is greater than any one of the children, we want to swap it because we want the lower element to be on top. So if this doesn't ring true, that means the parent, you don't even have to do current. Actually, yeah, we should do current. That's right. That's right. So if this is not true, that means the parent is greater than the current index. So what you want to do is you want to end up swapping them. So you want to say, well, okay, let me access the parent. I'm going to say parent index is equal to what's at the current index. And what's at the current index is going to be equal to, I suppose every loop we can just get this information. The element current index is going to be equal to, So wait a second. Maybe I want to do this is equal to values parent index, and then down here I might want to set this to element, and then set current index equal to parent index. Why is that so loud? Hang on one second. Being that JavaScript is my main language, we don't have immediate access to heaps and priority queues and well, I guess no language really has graphs, but you guys know what I mean. Uh, Binary search trees, all that. We have to create that. Stacks queues, we have to create it. Linked lists, we have to create it. There's no class for that. There's no built-in, standard template library like you would have in like C++ for JavaScript. So I've just grown more accustomed to just creating these things by myself. Now this should insert correctly. Before we actually do anything with, creating a node and doing it that way, I want to make sure that this works. So I want to create a minimum heap and see what happens if sorry, heap insert 4, heap insert, actually we'll insert what we have here, 1372, 1, 3, 2, 7, console log heap, or that value is just a property. Let's see if we can do that really quick, just to take a look at, make sure it's actually working. So this is good, because what happened was we end up switching it around. In this case, it's a 1, 2, 7, 3, but it's valid either way. That's just the way we enter the numbers. Like, if I enter it this way, that's different. Or if I, see 1327, that's still valid. If it's 1327, the idea of a minimum heap is that for each node, this is like a recursive definition, its children need to be greater than it. So the problem is that, yeah, this is greater than 1, and this is greater than 1, but this is less than 3. This needs to be greater than 3. So if I insert 2, what I have to do actually is swap them. That makes it correct, because then if I have a 2 here and I have a 3 here, well, now this is greater than 1, this is greater than 1, and this is greater than 2. Sorry, it's getting a little convoluted. But that's the central idea. So, how when I actually enter these values is going to influence, the specific direction inside of the specific position of elements inside the heap, or inside the array that represents the heap itself. But they're all equally valid in that we have 1 at the top. See, even if I move 1 down here, we'll still have 1 at the top, at the root. That's how we know it's valid. Okay. So as far as inserting a value, we should be good. Now the great thing about doing this is that we know the smallest number is going to be at the top. The smallest number. We may not know about the children. The children aren't ordered in any specific particular way. For example, if it's a binary search tree, we know, the element here has got to be less than this, and the element to the right has got to be greater than this. This is also a recursive definition, meaning the element to the left of 3 has to be less than 3. But every element has to be greater than 1. So it has to be greater than 1, less than 3. We can have 2 here. We can have 4 here. But it needs to be greater than, everything here needs to be greater than 1. And everything here needs to be less than 1. Now, things can be, less than or greater than 0, whatever. As long as ultimately it's less than 1. I have something on the left that needs to be, and okay, again, this is a recursive definition. Everything here needs to be less than 0. Okay? So, um, well, specifically, sorry, I didn't write that very well. Everything here needs to be less than 0. And so I can have -1. And then here, I can't really have anything unless I want to have 0.5 because it needs to be greater than 0, less than 1. You guys see the general idea. It's ordered in a very particular way. And you can have, because of this ordering, you can have things, you can have a tree that's unbalanced that ultimately becomes a linked list. It's not very, it's not very common, but it's possible. With a minimum heap or a maximum binary heap, either one, it's always going to be as balanced as possible. It's always going to populate from the left. And what I mean by that is we have 4. It doesn't matter which side you go. All we know is that these elements need to be greater than 4. That's the only constraint. So the constraint here is that it's greater than 4. That's really all it is. So we could have 7 here, 5 here. The next element's going to go here. The next element's going to go here. The next element after that here. The next element after that here. It's not going to, there is nothing that states that the neighboring nodes, so nodes that are neighbors to each other or siblings of each other, there's nothing that states that they need to be in a particular order. The only thing that needs to occur is that every node's children needs to be greater than that node. That's it. This can be 15. This can be 17. Doesn't matter. If this is 17, these nodes need to be greater than it. Now, as 16, you can even have 17 again. It doesn't really matter. Here's the thing. If I add a node that's like 2, that breaks the heap property. Because we look at these, they're fine, but 2 is less than 19. So what you would have to do is essentially you would have to move that 2 up here and then check these, this is exactly what I'm doing right here. Check this and its parent, child and its parent. And you're like, oh shit, okay. Let's move that. So now we have 2 here, we have 17 here. Let's check these 2. Ah shit, gotta switch them. And now we have 2 on top and 4 right here. Now this is perfectly fine. Children is greater than it, greater than it, greater than it, greater than it. That's perfectly fine. So that's really what we're doing here in terms of the insert. But we know that at any given point of time, any given point in time, the smallest element, if it's a binary heap, the smallest element is going to be at the top. All right. So another function that'd be useful is extract the minimum value. You can change this to node. I'm pretty sure that works. Extract the minimum value. So with this, what we need to do is, well, we can actually get the minimum value in the sense that that's what's in the front, right? And the end, pop. Now, if you try to extract values, the value and, and the length is equal to, the length is less than or equal to 0, we can return null. When we try to extract the value, what we're actually going to end up doing is, for example, let's say I have a, let's pull this out for a second. Let's say I have a heap like this, right? want to extract the value, what I do is I remove what's at the top. Boom. This is going to be what I return, right? I'm going to return that. I take the value that is the smallest out of these two. So first what I do is I take the end and I swap it. So we have 3 here. And that's pretty much it. So we like sort of rebalance it. But what if this is 2? Then I want this, right? So depending on which node is actually smaller, the smaller one is going to end up replacing the root and becoming the new lowest. Okay? So we have our minimum, we have our end. We're going to actually end up returning end. Now, if this dot values after you've popped, if this dot values dot length is greater than 0, still, then we can do our little thing. First thing we want to do though is we want to set 0, value at the top equal to end. And then we can call a function called bubble down. We can call it heapify down. Sure, that's fine. What we're actually going to do with this heapify down. And I don't even think, did we even use this? Parent? No, we didn't use that, so that's fine. Remove that, it's cool. Heapify down is going to, you know, after we place that, this is not really a good example. I need a bigger tree to really illustrate this point. So we have 1, 4, 7, 8, 9, 10, 5. So we remove, boom, right? And remove here. This is going to be our new root. We're going to return 1 after we're finished heapifying down. We're going to remove this. Now, we're going to put this where it needs to be. So we're going to take a look at the children. Take a look at here, take a look at here. The smallest one of this is going to end up being the swap. So 4 and 9. So 4 goes up here, 9 goes right here. We look at this, 10 is greater than 9, cool. 5, whoa, hang on there. Switch that. Got 9. Here we got 5. Now we're good. That's how it's going to work. So depending on which child is lower, so the child first, it has to be less than the parent. So at first, this has to be less than this, or this has to be less than this. If they both are, we pick the lowest one of the two. Since they both were, since it was only one, the 5 is the one that was less than the 9. That's why we swapped them. But if there was a 5 and a 6, we pick the 5. If there's a 5 and a 4, we pick the 4. So how can we do that? Current index. Yes, so current index is 0. Swap will come in clutch later. First thing we want to do is let's calculate the left child in the parent, which, as we said before, is going to be 2 times the current index plus 1. And to get the right child index, it's going to be 2 times current index plus 2. All right, cool. Now we need to check the element. All right, child. First, we need to see left child index needs to be less than the length. Here, let's create this. Sorry. Let's create this really quick. Let's say let length equal this dot values dot length. Sure. If left index is less than length, then what we want to do is we want to check if this dot values at left child index is less than this dot values at current index. And if it is, current index is going to be, sorry, swap is going to be equal to left child index. So at the end, we're going to swap them. That's it. Let's make sure that swap is equal to null at every iteration. Now, if right child index is less than length, we check to see if this dot values dot right child index is less than this dot values current index. But remember, there's a caveat. We want to go with the right child if it's less than current index and the left child does not meet our specific condition. So there was never a swap. If it does meet our condition, being that that left child is less than the parent, then we check to see if the left child is less than the right child. So this dot values so if swap exists and left child is greater, you could probably say and right child index, that value is even lower than what's at left child index, then we can swap. Or then we can change the value of swap. Now, if there's no swap, if there's a whole iteration with no swap, you can just break. Else, you essentially want to do the same thing we did here. It's essentially the same thing. We want to say current is going to be what's at swap. What's at swap is going to equal element. And now, current index is equal to swap. Now we keep doing that thing. So, here we go. I'm going to return the minimum. All right, here we go with that. So let's see. Let's see if this works. We're going to go console log heap dot extract min. And then let's see if this works. We should see 1 and then 2, whatever. So it did not work the way that I wanted it to. It did not. But that's because they go in as nodes. That's why. So let's push it in as just values real quick so we can see the basics. I want to get the basics first. Okay, so we remove 1 and it changed to 273. This is what we want. When we extract them in again, we should get 2 and a reformed heap. So let's see. Here we get 2 and we have 3, 7 left. Perfect. And you notice how it's not 7, 3, it's 3, 7. Perfect. Absolutely perfect. So now what are we going to do with this information? Now we can do the node thing. So we can make this like sort of a priority queue, almost, in the sense that now we're not just comparing the value there. We actually have to go dot val. So we have to actually compare these guys right here. And that's how we know to make the switch. So now it's dot val compare with that dot val. This is getting huge. This is getting really long. Here's what we're gonna do. Yeah, Jesus, that's getting really long. Let's damn. Okay, left child, right child, swap. So we'll let left child equal this guy right here. Right child can equal this dot values. Right child index right there. All right, so what we can do with that is we can essentially left child, right? Here we go. Left child. We can say this is now right child. Say this. Right child. There you go. Makes it significantly smaller. And we can leave current index the way that it is. I'm not really. Huh. Now this makes it different though, because this can go out of bounds. Let's put this here. Because then if it's here, we know that it's less than length and it won't go out of bounds. So I like this. This is a lot clearer. So yeah, so now if we do heap extract min, let's check that on out. It's still 3, huh? That's because here I'm not comparing it the way I'm supposed to. That's why. I have to compare on both ends, on the insert as well. Yeah. Because those are just indices. Comparing the value. Yep. Let's see if that fixes this out. Here we go. So we get 1. Cool. Very cool. And then I'm going to check console log heap dot values. So we should see 3 or 2. Crap, I always do that. And it's showing me the nodes we have left. All right. So from this, it shouldn't be that bad anymore. Because now we have a working heap. So what this means for us is what we really need to do is just for every single list that exists, let's create a dummy new list node with fucking 0, right? We don't even have to, because I think it's specified, or I think it defaults to 0, right? Yes, that's fine. Then we need the ability to traverse these nodes. Actually, I think what we can do is here, we can do this. It's crazy to handle lists like that, but for lists of lists, what we're gonna do is we're gonna take each list, we're gonna take each element. The thing is, I think I can do this without, because this seems very O of n squared to me, and I don't know if that's particularly how they want me to do it, but it might be how I end up getting it done. I want to go for each list. What I really want to do is sort of put every element in the yeah, we're gonna do it. So we can do heap Let me see the heap after this. Probably something vicious. Oh, sorry. I don't really like that. Here. Let's use like a. Honestly, it's not that deep. If you're gonna give me trouble like that, it's really not that deep. I don't really care that much. Let me just see what we got. Still not a number, not a number, not a number, not a number. Okay. Let's console log the list just to make sure everything's good. Okay. I know what to do. I know what to do. I know what the issue is. Let's try that. Yeah, there you go. So now the heap has 1, 1, 2, 4. But if we wanted to extract, we know the smallest one will be at the top. That's all we need to know. If we wanted to extract, smallest one will be at the top. So what can we do with that? Literally, we can do this. You guys are gonna be shook. Okay. What we can do is we can let head equal dummy. Head dot next is equal to heap extract minimum. Let's see what happens. Oh crap. Yeah, so this is gonna traverse everything for me. This is gonna traverse everything for me. Nah, that's crazy. That's crazy. The minimum heap. This question really is, can you use a minimum heap? A minimum binary heap. Can you create and use a minimum binary heap? That's all it is. That is all it is. The actual syntax of everything, the actual like nitty gritty functionality, stupidly short. Stupidly short. It's can you create a binary heap? Can you create a minimum binary heap? Because all the function, the heap is it's ordering everything for me. Like when I insert, it's in order. When I extract, it's going to be in order, such that the element at the top is always going to be the minimum. It's doing because it's doing everything for me. That's it. That's super cool. And I did it in 41 minutes. I mean, that's not particularly fast, but there we go. There's a freaking problem for you, man.